instructions in my copy. Oh. When I was thinking this year, they don't call it. They cancel it.
No, they can't.
I filled a bucket of water with soap for them to clean out their materials.
Yeah.
They just dunk it in there and they don't wipe it or rinse it.
No, I know. They're feral.
They just put it on the sink and then just leave it. So I don't know who the is.
Any questions before the quiz? I know your quiz is not today. If you're like, oh my God, it's a quiz today. It's not today. I just want to know if anyone has any questions related to tomorrow's quiz. Anyone? Going once, going twice, going 3 times. Sold. Okay, good. In that case, if anyone came in late, come see me to get the second half of your black workbook. I will also, by tomorrow, have an updated cover page for you, so you can actually look up where the sections are by page number. But right now, we are on page 59, 59. Okay, we're not going to watch this video because I believe it's just me teaching, so, no real point in that. It's just in case if you were away or something and happened to have this. So when we mix a strong acid, SA, and a strong base, SB, page 59. The two are going to neutralize one another. And when we put a strong acid and a strong base together, we get a salt, and we get water, and the salt does not hydrolyze. Because who's the acid that gave us the anion? Hydrochloric, right? Which is a strong acid. And yeah, so unless you had chromium or something in there, which is very unlikely because chromium hydroxide is not soluble, so that would not be one of your strong bases. Okay. So depending on the quantities present, either you have neither the acid nor the base in excess, and of course that means it is neutral, pH 7. If there is excess acid, can you guess what the pH will be? It's shockingly difficult. It's acidic. pH is less than 7. Whoa! And if there is excess base, it's basic. Oh, okay. So now we're going to do some actual calculations around this. When 10 milliliters of 0.1 molar HCl is mixed with 10 milliliters of 0.1 molar NaOH, if you had to prove this using calculations, you could say, okay, well, I can take my volume. Remember, of means times molarity. And you get 1 mole of H for every mole of HCl, so you get your moles of H plus. And then you do the same thing for your NaOH. It ends up being the same calculation because you have the same volume and the same molarity, and you end up with moles of OH minus. Could you write a net ionic equation for the reaction of this acid and this base? what is the net ionic equation for any strong acid, strong base? H plus plus OH minus yields H2O is good. And you would take your little... Now, I'm going to introduce you to a new table. It's almost like rice, but it's the RICFA table. RICFA, which is not nearly as lovely as rice, but what you do with it is you're going to be dealing with reactions that go to completion. Yes? Okay. Do you need to go to the washroom? Do you need to go like...
No, I said I don't think it's a bad idea. So
Okay, okay. So this reaction goes to completion, and I know this is like the simplest example of this because we're going to use it, because the moles are the same, we're going to use them all up. So you write down your initial moles of H plus, you write down your initial moles of OH minus. Because they react 1 to 1, and because the moles are the same, we're going to use them all up. Yes? So we're going to end up using up minus 0.01 and minus 0.01, and we get our final molarity of H, and OH is 0. And of course, we do have some moles. Oh, and that's the other thing I forgot to mention about the RICFA table. I'm sorry, that's a terrible name. Is that we can do it in, I generally tend to use it in moles, not in molarity. So your rice table is always going to be in molarity because rice is related to a K value because it's an equilibrium, and K values are always calculated in concentration. So rice tables will always be in concentration. But we can do RICFA tables in moles. And you'll notice I have written moles, 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 moles. Okay? The RICFA table. If anyone comes up with a better name for that, I would be thrilled to hear it because it sounds really stupid. At any rate, yes?
here we go.
Okay.
Still the rice table, but E stands for N. What?
I kind of like it, but people will get confused. I do like it, but I think people will get confused. So we're going to just go with the... Yeah. Anyway, keep your mind percolating on that. I will also keep mine percolating, and we'll see if we can come up with something a little nicer. But if not, RICFA works. Kind of, sort of, icky, but there we are. There is no hydrogen. There is no hydroxide, and therefore the pH is 7. The main reason to go through this example was just to show you how this RICF table worked. Okay? So let's do a situation where the moles are not equal. Page 60. And we are going to spice things up by using millimoles. If you hate millimoles, too bad, we're going to be using them. It's going to make your life so much easier when you are doing buffer calculations, when you're doing mixture calculations. It will just make your life nicer, okay? And the nice thing is that you just take the numbers that are given in the question. So if we're talking about finding our hydrogen ion, then we're looking at our HCl. So we're just going to take the numbers given in the question, 10 milliliters and 0.1 molar, and we're going to multiply those two together. Look at that, 10 milliliters, 0.1 moles per liter. Yeah? Then, of course, in HCl, we have 1 H plus for every mole of HCl. We do our calculations, and look at the math on that. 10 times 0.1 equals 1. right? Is that not nice math? You end up with a lot of nice numbers like 6, 4, 1, right? They're just nice numbers rather than 0.004 or 3.2 times 10 to the negative 3. They're just tidy, nice little numbers, okay? And then, of course, hydroxide. We have 90 milliliters. So here's our 90 milliliters. And we have 0.1 molar. Yes? Oh, that's because apparently I just can't do, I was copying and pasting and did not copy and paste correctly. I copied and pasted and then did not replace.
I was looking at it.
You're like, what? How? No, because this should also be beautiful, easy math. And what should the answer be? 9. I promised you nice, easy math, and then I gave you some ridiculous thing. Yes? And you'll notice, here's the milli here. Milliliters gives us millimoles. Milliliters gives us millimoles. Yeah? And once again, we're going to use the net ionic equation, which is always H plus OH gives water when we're doing a strong acid and a strong base in our RCFA table. So here is our initial. I haven't written everything because I'd like you to look at that table, which has a beautiful 1-to-1 ratio, and tell me which reactant will get all used up. The H plus will get all used up, yes, because there's less of it and they react in a 1-to-1 fashion. So H plus will get all used up. That is our limiting reactant. That means what will we have left over at the end? OH. So we're going to have a pH greater than 7. And we can just do the calculations at this point. So we're going to have OH minus left over, and we're going to complete the table so that we know what we have. We started with 1 and 9. And of course, water has 0. And this time we're working in millimoles. So you can either write the millimoles here, or if you want to, you can write the millimoles here. Whichever one is easiest. I kind of find it easiest to put them on the I's and the whatever, but it doesn't matter. If you want to write them in the thing, you can do that, okay? So how much of the H plus is used up? Well, all of the H plus is used up. So that's going to be our change. And, oh, yeah, that's right. And so how much of the OH minus is used up? The same amount, because it is 1, 2, 1. We do our math and we get 8 millimoles of OH minus left over. And then, I mean, you could, I have included water in this RICF diagram, RICF table, but the water is optional because will it make any contribution to our acidity or basicity? Will water make any contribution? No. So you can, if you want to, instead of writing everything out, you could just do, do you know what I mean? You can just do like a little squiggle under it saying, I'm not doing anything for that because it's irrelevant. Okay? Once you have your millimoles of OH, you're going to find concentration of OH, POH, and then pH, or concentration of OH. Oh, I did not write it differently. What should I have written here? Concentration of H plus. There's a lot of stuff in here that just got done over the weekend, so we'll probably find lots of boo-boos. Fun times. Okay. Where was the other one I did that was wrong? Here. Fix. Fix. Okay. Now to find the concentration, you need to take your moles of OH left over. And you're going to divide by the total volume. So we're not actually using moles, we're using millimoles. So we have 8 millimoles. And our total volume, this was the volume of the HCl solution, and this was the volume of the NaOH solution. So that is our total volume altogether is 100 milliliters. And again, look how lovely and easy this makes the math. I have 8 divided by 100, which is 0.08. Like I can do all of this, a lot of this I can do in my head if the numbers are nice and round. Yeah? So there is our answer. Then either find your POH, find your pH. I'm just zooming through this because I assume you guys know how to do that at this point, right? We're good with that? Okay. Or you can, and this is the one that if people are going to forget that this route is possible, so if you were asked for what the hydrogen ion concentration was, I could do that. I could believe it like, what's the hydrogen ion concentration? And many people would get confused because they'd be like, oh, I don't know, it must be 0, right? Because I used it all up. Ha 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 ha. But remember, there is still hydrogen from the auto ionization of water. So yes, there's no extra H plus left over from the reaction. However, we still can find the concentration of hydrogen based on the fact that Kw divided by 0.08 is 1.25 times 10 to the minus 12, which makes sense because that is less than 1.0 times 10 to the minus 7, which is the concentration of hydrogen in pure water. Or I'm sorry, yeah, water. Is good? Okay, cool. Oh, and then we've hit exercises. So we're not going to do that. We're just going to keep moving. We'll let you do that after your quiz tomorrow for homework. Okay? Mixtures of strong acids and bases, part 2. So this is a summary of what we did on the last worksheet. Calculate the moles of H plus or millimoles. Calculate the moles of OH minus or millimoles. Determine the limiting and excess reactants. Find the moles of H or OH in excess. I'm going to recommend that you use the RICFA table just because it is a really good structure. However, there are definitely ways to do the calculation without using that whole table. If you can just see in your head that you're like, oh, I just need to take this number and subtract that number, as long as you've labeled everything, that's also fine. Okay? Kind of optional, shall we say? And by kind of optional, that just means use it unless it feels more cumbersome than helpful. Yes? If it's helpful, use it. If it's not helpful, don't. Yes?
No marks off.
No marks off if you don't use it. And in fact, you'll see when I've done the answer keys, which I don't have for you today, again, that will be here for you tomorrow, but you're not doing anything in this for homework today, so you don't need the answer key yet. Answer key will be ready by tomorrow. When you see the answer key, very often I do it both ways. I do just, here's how you find the excess, and then I'll also use the RCFA table to show the work. Yes. All right. Find the final pH. When 50 milliliters of 0.2 molar HCl are mixed with 50 milliliters of 0.3 molar barium hydroxide. Now, one thing you're going to notice here is, what do we have? We have two OHs, and this is on page 62, page 62. So let's write a formula equation. I'm hoping that would this formula equation be easy enough for all of you to have written? Yes? Okay. So we're just going to leave it at that. All right. And then we would have to balance it, of course, because you must have a balanced formula equation. And then the question is, does that affect our net ionic equation? Well, if we do our complete ionic equation, we split the H and the Cl. We split the barium and the hydroxide. We split the barium and the chloride, and then the water stays together. So guess what? What do we end up with when we cancel our spectators? Spectator. Spectator. What are we left with? 2H plus 2OH gives 2H2O. Would you leave it like that? No. So guess what? It doesn't matter that there's a 2 in the OH. The net ionic equation is the same. So the net ionic equation is the net ionic, this net ionic equation is the net ionic equation for all strong base acid, strong base neutralizations. I think the one exception might be with H2SO4, but I think even with that one, because it's the diprotic acid and the second proton is weak, but you could get away with this because I've seen it in AP answer keys where they're just like, yeah, just rip them both off at the same time. Okay, so don't even worry about it. If it's strong, just go with it. Okay, so here's our going through the process. Calculate moles of H plus, and I actually ended up calculating millimoles of H plus, 50 milliliters of 0.2 molar HCl, 50 times 0.2, and there's 1 H, so that's 10. For our millimoles of OH minus, 50 milliliters times 0.3 molar, but now we have, this is where the 2 comes in, okay? Now we have to, when we're calculating the moles or the millimoles of barium hydroxide, that's where we use the 2. So we have 30 millimoles. We use our net ionic equation in the RCFA table. How about rice is fine? Rice is fine? I don't know. Anyway, I don't know. I'm not going to fix this problem today, am I? Nope, I'm not. Here are our initial quantities. The lovely thing about any of these is that they're all going to be 1-to-1 because the reaction, the net ionic equation is always that 1H to 1OH. So the math is going to be super simple, always, okay? So we have 10 millimoles of H and 30 millimoles of OH. Who is the limiting reactant? H. So we are going to end up with a basic solution at the end. And what will we use as the change? we'll use the amount of H as the change. So let's go do that. Here we are, our change, we're subtracting 10 millimoles. On the water side, we are adding 10 millimoles. You'll notice I've written millimoles, millimoles, millimoles to let them know what my units are. And when we do the subtraction for hydroxide, we end up with 20 millimoles of OH minus R in excess. In other words, that's how much R left over. Your total volume is 100 milliliters. So you can now find the concentration of the thing that's left over. Total millimoles of OH over total milliliters, 20 over 100, because we had, what, 30 and, what were our volumes? Volumes were 50 and 50. So yeah, total volume's 100. Then we've got our concentration of hydroxide, and that's it. Is good? There wasn't really much that was different on this one. I just felt like breaking it in two. Okay? All right. Ready to move on to some weak stuff? Or do you want to try a few practice problems? Practice problems? Okay. So you could start with, I don't know, why don't you do the questions on page 64? Because I feel like this one is very similar to the last one we just did. It has barium hydroxide with OH. So maybe try number 2 and 3 there on page 64.
Oh my god. Oh my god. That vehicle product is sandy wood. Oh, I'm thinking about that. But the bean said it was the same. We're coming over the end of the tax.
Oh, okay.
I thought it was San Diego popping off, but it's actually San Diego.
Oh, yeah, yeah.
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 What's he said?
Yeah.
All of the input was there on that last thing, the wrong.
Oh.
That's so sad.
Daniel, what's the molar mass?
Peter Walker, is this your phone?
Oh, yeah.
It's too nice? Evan says it's too nice to be yours.
Yeah.
They're like, somebody left their phone, it's not your phone. It's not. There you go. Ah. Yeah, there's the fucking.
Then how do you get on the learn?
Yeah. So it doesn't matter if you, yeah, you just need moles.
Also, like, those actors, all that shit.
You could. That's exactly it. You can, I mean, you can like the table with Mueller if you want, but I feel like it's just a kind of stuff. It's good. I have an answer to my question.
I have a. I can find all the data. That's pretty good.
Oh, that was data.
I got. I got cars. That's like. Nothing could have made me get that hard.
Oh,
Except maybe if I sat alone.
which one is this? 5.4B. Oh, the answers are at the bottom of page, whatever the next page is, 65. The answers are at the bottom of page 65. So if you want to check. Worked answers are in the key, but. What? Why don't I have 2 and 3 in here? What the hell? Oh. That's strange. Okay. 5.4B needs key for 2 and 3. Worked key anyway. So strange. 1, 2, 3, 5. 1, 3, 4, 5. Oh no, I think these are okay. They are the same. I've just not numbered them properly. Okay. Did you guys get number 2? 1.696? Or did I get it wrong? So how you would show your is say your moles. Okay, so you would say moles with that figure. So you would say moles equals that equals that minus that. Oh, yeah. Probably. Yeah, I think probably. Or it's possible I made a mistake too. This is brand new. So let me know if I made a mistake, okay? Check your answers with your neighbors. Hello. No, you can just use this to find moles and then this will be from your goal. When it, at the end. You think you see what's wrong with it?
Like, I got the right answer, but it's like.
What were we supposed to have found? Were we supposed to have found pH or POH? Oh, POH. Oh, for goodness sake. I only found the pH. Yeah, okay, so if we were to find POH, we would take 14 minus that. Okay?
Yeah. That's like the last one.
Wait, no, I'm.
Are you guys getting 12.304? Is that better? No? Oh. I'm probably doing something wrong here, so we'll see. Oh, did I multiply by 2? I did multiply by 2. Okay. 1.85, 1.85. Yes? That's what you got? Yeah! Okay, I'm gonna go with that. So you should have gotten in your rice table or RICFA table, that's what it should look like. Unless you're doing them in moles rather than millimoles. These are millimoles because I don't like times 10. Otherwise, it'd be all these numbers times 10 to the negative 3. Yes. Here, hang on. Hydroxide. So I found the moles of strontium hydroxide, which is 0.925, and then I doubled it. Yeah? Yeah. If you got close but not exactly the same answer, it's probably just that you rounded a little early. But you got the same answer, right? Yeah, cool.
Yeah.
You're good? Very good? Cool. Have you guys done number 3 now? Okay, try number 3.
Okay.
And I'll put up the answer.
Oh,
Is that good? Let's see. Okay. You only have 2 decimal places here. You only have 2 digits. So your answer is going to have 3. So you need to keep at least 4, sometimes 5. As we discovered, I've come across a couple problems. Stephanie came across one. I came across another where we had 2 digits after the significant ones ended in order for the calculation not to end extremely. And I just came across another one when I was doing it. So I'm like, great, that's awesome. Yeah. So keep 2 digits after, and then you're good. Actually, I was looking at somebody's answer key over the weekend. They called them guard digits, and I like that. So keep 2 guard digits. No, I think 2 guard digits should do it. Fingers crossed. I honestly really like. I mean, 90. I would say probably 99% of the time, 1 guard digit is okay. But if you get that 1% where it's not, it pisses you off. You're like, I would did yeah. Right? Yeah.
We don't have to use normal.
You do not have to use normal. You can use regular moles. Yep. Yep. I'm lazy, so my answer key will be a millimoles. But yeah, you can always just tack a 10 to the negative 3 on it and you're good to go. So number 3, you should be getting 0.557, I think. Let me know if I'm wrong. But I could be wrong. Is it you who's wrong or me who's wrong?
I think that's the answer key for number 4.
Oh, that's number 4. Okay, never mind. I think I've really screwed up on the answer key, which means it's actually a really good thing that I haven't printed the answer key yet. So I can fix it for you before we get there. Yeah.
I don't know what it is.
Okay. Okay.
The whole discussion is so easy. I don't have to do it.
Oh, yeah. Oh.
You are.
Yeah, no, you're good.
Oh, I see.
Yeah, it's just
what?
Yeah. Yeah.
Oh, it's a bit of a wise thing.
It shouldn't be, but it's there to like kind of like, remind you. Yeah. Okay. So you could try number 4 as well. Okay. And I'm going to try and find. Two.
Yes.
Okay, 3 is a dilution, not a thingy. So if you tried to RICF it, it won't work. So 3 is a dilution, and then this is number 4. I think 3 is missing. So I think this should be, God, what a horror I've given you. I think it should be number 4, right? Do any of those other answers look like the answer key to number 4? What's 5? Okay, that's 5. Is this number 3? For number 3, you got 6.25 times 10 to the negative 14? Yeah! Okay, I got something right, just not the right order. Okay.
Let's go.
Yes. Why are there 3 sig figs in that one? Well, let's go take a look at the question for number 3. I've got, oh no, there should only be 2 sig figs. Yeah, there should only be 2 sig figs in that. Yeah, you're right.
Yeah. He was wondering about them.
So can you find this? Yeah. Dude, it's cheap for someone else.
That's okay. I need a break. Why? I'm going to move it to Friday. No. Oh, it's funny. My dad was so young.
What?
I know.
Hey, I don't think okay, so then just figure it out first and then do your final. Is it your final at 12?
It is.
No, think about it. If you solve crypto's logbox, you'll be like, oh, I'm a menace. We're going into this test.
No, I passed.
Oh, so that means you're chilling.
I'm just unable to solve it. I wish I could create this.
What do you do? Is it bring your own goal?
Bring your own goal. That's why I'm
Are you gonna hit a low? What are you gonna call? Ask Chad.
It's 6.3. Yeah, I haven't fixed that yet. There we go. 6.3. There we go. There we go. Does that look better? Yeah. Okay. Good stuff. Two, 4,
Yo,
3.
Elvin,
There we go.
you sit in a suitcase bro, surrounded by dead bodies.
Yeah, bro. No, I wonder what it was. I don't know. I don't really understand. Huh?
Most of the front of the town.
Three, 4, 5.
Yeah. What else?
5. Steve, is it everything left? Oh, stupid computer's being stupid today, but that's okay. File, save. Okay, we're gonna compose that. No. Okay. All right, are we ready to learn something new? Little something new, but it's just kind of more of the same. Okay, let us go to, yes. Let us go to mixture of weak acid plus strong base. Weak acid plus strong base, and then we'll move into weak base plus strong acid. We're not going to worry about weak base plus weak acid because unless we're doing a buffer, which we'll learn about in the next section, we're not just going to have a random weak base with another random weak acid, okay? And buffers are their own special thing, so we're not going to worry about them. Okay, we are on page 66, page 66. And what I would like you to do is I would like you to take a look at example number 1 and see if you can write the formula equation, the complete ionic equation, and the net ionic equation. Do it in pencil because I will check with you afterwards.
Was it? Yes. What is
Okay, I'd like you to check your formula equation. Make sure you have your states in there, okay? And when it comes to writing the complete ionic equation, I want you to remember, take care remembering what happens with weak acids in solution, mostly. The weak acid stays mostly intact. Remember, they only dissociate a very small amount, so you do not dissociate the weak acid. One other thing I would like you to take note of, what kind of arrow do you see here when we are reacting the strong base with the weak acid? It's a completion arrow. Why is it a completion arrow if CH3COOH is a weak base? We have a strong base and we have a weak acid. That is just how it works. But basically what happens is if you have OH, yes?
Because with that Elliott principle, so then concentration is what you think, so then it results more after the increase,
that is definitely one way to explain it. Okay, it is a good way to explain it. So yeah, you can use Le Chatelier's principle to say if we consider the equilibrium of CH3COOH in equilibrium with H plus and CH3COO minus, if we add OH minus, what do we get here? We get H2O, which means that that concentration is dropped, which means that this shifts to the right, and that just keeps happening as long as you add OH minus. Yes? The other way to think about it is that the strong base just goes around and rips all the hydrogens off of the weak acid. So as long as there's an OH there, it will rip off the hydrogen. The OH is a stronger weak base than CH3COO, so it will rip the hydrogens off of CH3COO. Okay? But yeah, however you want to remember it, you're not going to have to explain why it's a completion reaction, but you are going to have to know that it's a completion reaction, right? So if you understand it, that does make it easier. So you can think of it like using this equilibrium here, and it'll be shifting to the right, or you can imagine that strong base ripping all the hydrogens off of the weak acid. Okay. Who are our spectator ions? Na? Anything else? Nope, nothing else. So our net ionic equation is OH minus plus CH3COOH goes to CH3COO minus plus H2O. So you can see that unlike in a strong acid, strong base neutralization where the equation is always going to be the same, when you have a strong base, weak acid, it'll be different. You'll have different acid species. You'll have different base species, okay? Now, I got really, really lazy here, and I didn't even leave room to calculate the millimoles of hydroxide and of CH3COOH. And that's because I gave you lovely numbers. Because we have, how much of the OH do we have? We have 2 milliliters of 1 molar NaOH. Can you just in your head figure out what the millimoles of OH are? 2, yes? Because you just go 2 milliliters times 1 mole per liter is 2 millimoles. So we're just going to throw that in here. If you want to show the work somewhere else, you can, but you'll get lots of practice doing that on the previous worksheets, okay? So we have 2 millimolar, and I'm not even going to bother with like decimals and stuff. I'm just going to throw a 2 there just to make our life really simple, okay? The CH3COOH, acetic acid, we have 8 milliliters of 1 molar. So how many millimoles do we have? We have 8 millimoles. Okay. And we have 0 millimoles of the conjugate base, and we're not going to worry about water because it's irrelevant. Could you fill in the change and the final? Did you guys get 0.62 for your final row? Excellent. So now what you're going to do is you're going to say my only species that are left, I have the acetic acid and I have the acetate ion. So you're going to find the concentrations for those so you can use them in a rice table. Ooh, we're back to rice. Why are we back to rice? Because you have a weak acid and its conjugate base, and those will be in equilibrium with each other. So we take our millimoles of CH3COOH, that is 6 millimoles over, what's our total volume? 2 milliliters plus 8 milliliters. Did I tell you I was being super nice with the math? 10 milliliters equals 0.6 molar. Yes? How lovely. And then the CH3COO minus, we have 2 millimoles out of 10 milliliters, which is 0.2 molar. Oh, look at that. Now, we have both, the weak acid and the weak base. That means you can either use the weak acid equilibrium or you can use the weak base equilibrium, and it really actually doesn't matter which one you do, you'll get the same answer. Now, usually you're given a Ka value rather than a Kb value. Which one would you choose if you wanted to do less work? The weak acid. Now, if you were given a base and given a Kb value, you might choose to do the weak base equation, right? Could you please write your weak acid equilibrium and then draw a rice table? It is optional to put the water in there. Yeah, you could just do it with H rather than H3O plus if you were feeling not very energetic. Okay. And in fact, I'm going to do that down here because why not? CH3, COOH. So I've just used the simplified version in the race table. What is the initial concentration of acetic acid?
0.6 molar.
0.6 molar. What is the initial concentration of acetate? 0.2 molar. What is the initial concentration of hydrogen? 0 molar. Are we following why we got those? Mostly, like we ended up producing, we didn't use up all of the CH3COOH. We produced some CH3COO minus, and the H3O plus, just, we assume it sits at 0 until these guys get busy and react. Okay? Now, what is the change? X plus X plus X, and over here we have minus X. So now we have 0.6 minus X, 0.2 plus X, and X. Here comes our Ka. Write your Ka expression. Plug everything in. You can look up the Ka value on your table. Whoa, what do you guys think of that? Do you want to do a quadratic?
No.
No, what could you do to avoid a quadratic with this thing here?
What?
You could assume that X is much, much less, or X is insignificant. Yes, we're assuming that it's much, much less than 0.2 and 0.4, and that gets rid of these little X terms there. And now we have something that's easily solvable. X is equal to blah, blah, blah. There's X. Whoops, because I said H, I should put a molar there. And pH, I didn't even bother showing the work because I feel like at this point you guys have done so much of that, we're just going to kind of be like, okay, you could do that. And here we are. Okay, so that gives you an introduction to that. When you have a strong acid, weak base, you end up doing both a Ricva table and a Rice table. And we will do more on that. Probably not tomorrow because we've got the quiz tomorrow, but definitely the day after that. Okay? Yes. Well, it depends on how long it takes you. I always think it should not take the whole block, and then you all take the whole block. So, you know.